Welcome to this presentation on graphs. It turns out that the linked lists and binary trees that we've looked at so far are actually special types of graphs. In other words, a graph is a more generic data structure that allows for a lot of different shapes and connectivity. Basically, a graph is a collection of vertices or nodes and edges that connect them. So one good example of a graph would be an airline's flight route map. So you can fly from one city to another city and then from there connect to other cities. This is kind of similar to how graphs work as a collection of vertices or nodes and edges or paths. They have a concept of a node's degree, and that is how many edges or paths are connect that node. So for example, the degree of A is 3, 1, 2, 3, because there's 3 paths coming out of A. And then the degree of E is 2, there's only 2 paths coming out of E. So there's a little bit of terminology associated with graphs. Graphs can be directed or undirected, meaning if there's no arrow on an edge or a path, it's assumed that you can go either way. So this one is an undirected graph. You can go from A to B or you can go from B to A. Some graphs are directed graphs. Sometimes they shorten that and call them digraphs, and that means that each path has an arrow associated with it. So you can go from A to B, B to D, D to C, and so on. But notice that once you get into this loop here, this DCE loop, you can't get out of it. You can't go back to B, you can't go to A. There can be some uses for this. One possible use of this is to represent a state machine for a game. You start off at a certain point in the game and you go to someplace else, and for whatever reason you're not allowed to go back. That's a possibility. How do we store graphs in our computer programs? There are two most common representations or storage of graphs are an adjacency matrix and an adjacency list. And we'll look at an adjacency matrix first. Adjacency matrix is really what it sounds. It's a two-dimensional array of entries that represent the edges. So along the rows, we consider a number of rows to be the same number of nodes or vertices in the graph, and the number of columns to be the same number of nodes or vertices in the graph. So an adjacency matrix would be a square matrix. And if there's a 0 entry, that means there's no path. So from A to A, there's no path. There is a path from A to B, and there's also a path from B to A. So we would have to consider the rows as maybe being the from and the columns as being 2. But if this is a undirected graph, then it's going to be symmetric, so it doesn't matter, meaning you're going to have a path from A to B and B to A, so it doesn't matter whether it's, the rows are from and the columns are 2. It doesn't matter for an undirected graph. For a directed graph, it does matter. And so here I've labeled the columns as being the from node or the from vertex, and the columns to be the to node or the to vertex. So for example, we can get from A to B, so there's a 1 there, but you can't go from B to A, so there's a 0 here. And so it's relatively easy to search or look up a node to find what other nodes it's connected to. Or if you have 2 nodes, you can find out if there's a path going from that node to the other node. The other way of representing graphs is what's called an adjacency list. And this is basically a list of lists. So for each vertex, you will have a list that just contains all the nodes that are connected to it. So the A list would just have B, and notice that the C list would have B, D, and E, because C is connected to all those nodes of vertices. Over here in the directed graph, it's a little bit different. The C list, you can only get from C to E, so the C list only has E in it. B is the only one that has more than 2 edges coming from it, so you can go from B to C and B to D. So in the adjacency list, it's a list of lists. For each vertex, it tells you which nodes you can go to. So that's the adjacency list representation of a graph. Sometimes graphs, their paths or edges can have weights or cost associated to them. So for example, a airline's flight route map might have miles associated with each flight. So to go from this city to that city, maybe 500 miles. To go from this city to this other city, maybe 800 miles or something like that. Here we have a series of numbers, and maybe they represent costs. Maybe to drive from here to here is 9 miles, to drive from here to here is 6 miles, to drive from here to here is 15 miles or something like that. So there can be costs associated with graphs. So for example, to go from A to B to D, to go from A to B has a cost of 7, and then to go from B to D has a cost of 15, so that gives you a total cost of 22. Is that the cheapest cost? And maybe it is and maybe it isn't. In this particular case, it looks like we can go from A to C at a cost of 9, and then C to D at a cost of 11, so that has a total cost of 20. So it may be cheaper to go this way. And this is how, if you've ever used a GPS system or Google Maps or something like that, get directions, often you can choose a particular criteria, and the map will adjust the route based on your criteria and based on the cost involved with your criteria. So sometimes you can do a search for directions that'll give you the shortest amount of time, and that could vary with the traffic. And then other times you may want a route that has the shortest distance, which may not be the shortest time due to speeds and traffic and so on. So you can change what type of cost you're looking for, and you might get different paths, different directions from a map, say. To traverse a graph is a little bit more complicated, and there's several different graph traversals. The two that we'll look at are what they call breadth first search and depth first search. And the basic idea is you start at a particular node, so a breadth first search starting with A. We start at A, and what we want to do is to process or examine all the nodes that are one step away from A. So then we'll be processing B and C. When we're done with that, then we go to the nodes that we just processed, and we process basically nodes that are 2 steps away from A. So now we'll be looking at E and D, and then 3 steps away from A, we'll be looking at F. And we don't want to duplicate any nodes, because if you do, then you can end up in a loop. So, you could say that, well, B is 2 steps from A, so we go to A, C, B, and you can end up in a loop, and you don't want to do that. So you would make sure that you don't duplicate any nodes during that process. In a depth first search, it's a little bit different. We want to start at a particular node and go in a direction till we get to the end. So go in a particular direction and we can't go any further, and then go back to that node and go in a different direction. So for example, if we start at A for a depth first search, we may get A to B, and then B to E, and then E to D, and D to F, and we can't go anywhere without duplicating or revisiting a node. So then we go back to A and go in a different direction. So we go from A to C. And again, we could go to B, but we've already seen B. We've already visited B, so we don't want to duplicate it. So then we're done. And that's the end of the depth first search for graphs. So we will stop here and look at some code for implementing a graph and implementing searches in a subsequent presentation. Let me know if you have any questions on this graph concepts and terminology.